Okay, let's get started. Lecture 4. We've made it through the first week. Homework 1.2 is due. That one was probably a little bit more challenging than the last one, but hopefully not too bad. And the grade should have been visible after you did it. Did that work? Okay, all right. That'll be the last of the assignments that we have that are in that quiz format, as it were. So after this, from here on out, there'll be scanned PDFs. So the idea is that you will do the assignment on, engineering paper or white paper or something like that, and then you'll scan it and submit it via Blackboard. In my first set of lecture notes, I go through step by step how to do that. I show you how to do that using an app called Cam Scanner, but there's oodles of apps you can do that with. I'm actually starting to prefer Microsoft Lens because I can scan something and it'll go right to my OneDrive directly. So it makes it a little easier to manage things. I did post the attendance grades on Blackboard. They are there now, so you should see your attendance grade. So my goal is to try, now that we've gotten through the first week, to try and handle that a little bit more regularly. There's also a folder called Older Homework Solutions, and that folder will contain that folder will contain the homework solutions as we go. So right now, the only homework solution is homework 1.1, but the idea is that maybe by Wednesday, homework 1.2 is available. Yes? If you don't mind, can you put a QR code? Yeah, I was going to say something about that here in a sec. So let me go ahead and pull the QR code up. Does everybody have that? Everybody get it? Everybody got it? Okay, so this last week, I didn't count anybody late, just because it's the first week and everybody's getting in the swing of things. I'm probably going to start doing that, and so I'll leave the QR code up maybe for a little bit to make sure that everybody comes in. But if you don't get the QR code scanned at the beginning of class, I'll pull it up at the end. But for those that scan it late, I'll probably count you late, which is like half of an attendance point and whatnot. Just make sure you're here on time so we can get things rolling. Everybody good on this? Any questions? All right, so we're actually going to begin today's lecture. In today's lecture, we're actually going to start talking about statics. And what I mean by that is the past week has really been sort of just getting everybody up to speed on the basics of the physics and the math necessary to negotiate this class, but we haven't actually talked about statics. So let's talk about statics. I'm going to go back to some of the earlier discussions I had to sort of define like what physics is and what mechanics is. But what we're going to spend the pretty much all of today's lecture on is the discussion of a very important mathematical concept in this class, which is the idea of a vector. Vectors are incredibly important to what we do here in Engineering 213, and if you don't believe me, just look at the title of your textbook. The title of your textbook is Vector Mechanics for Engineers, and that's not just a creative title. Vectors are how we go about assessing this course, as well as dynamics and some other later courses in engineering. So we need to talk about that. We need to come up with some rigorous definitions that we can hang our hat on, as it were. So let's get into it. If you remember on day one, I first went through and I said, okay, what is physics? Okay, and physics is, generally the study of matter and energy and the interaction between them. But then we went through and we said, okay, there's oodles and oodles of different areas of physics, and what we're focusing on in here is mechanics. And mechanics can generally be defined as the study of forces. In other words, I have some system, some body, I apply a force to it. What is this response? How does the system react? And so on and so forth. And that's generally what mechanics is the study of forces. Okay? So what we need to understand is how are we going to mathematically deal with forces? Okay? And so what we do in mechanics and in the associated mathematics of this, we have sort of two terms that we are going to start differentiating real quick. Okay? And those are the concepts of scalars and vectors. Okay? Now, a scalar is a mathematical object that contains only magnitude. In other words, a scalar is just a number. Okay, so 6 is a scalar. Pi is a scalar, and so on and so forth. And just to be clear, we're not getting into imaginary land or anything like that in this course. Okay, so a scalar is a mathematical expression that contains only magnitude. And there are physical representations of that: volume, temperature, area, mass, length, time. Those are quantities that would be represented by a scalar. Anything that contains only a magnitude. Okay? Whereas we also need to define a mathematical object that contains both magnitude and direction, and that's a vector. Okay? Because what we're going to be dealing with is we're going to be dealing with systems, and they're going to be subjected to forces. There's going to be a force here, a force here, a force here, a force over here. And so we're going to need to know the magnitude of those forces and the direction in which they act. Do they act this way? Do they act that way? Do they act that way? This way? And so on and so forth. So we need to be able to define both the magnitude and the associated direction of these given forces. And that's what a vector is. It's an object that contains magnitude and direction. And again, forces, there are examples of that, but there are other examples of that as well. Velocity can be represented by a vector. Acceleration can be represented by a vector, and so on and so forth. Everybody with me on that? Now, let's talk about notation. Okay, so if you open your textbook, and this is coming out a little weird here in the slideshow. I don't know why it's coming up with this T or whatnot. But in your textbook, what you will primarily see in your textbook is that vectors are represented by bold characters. Okay, bold characters being pretty easily identifiable on a textbook. And so if you remember, in one of my previous lectures, I had some discussion about velocity, acceleration, and position, and I had those terms bolded because they were vectors. They indicated both magnitude and direction. Now, I don't know why this is coming out a little weird. I don't know if it's because I'm pulling this up on the slideshow or on my browser and whatnot. What this is supposed to look like, this term right here, let me pull up my notebook. What it's supposed to look like is like that, something like that, or that. More often than not, when I'm writing, I will utilize this terminology to describe a vector. Every now and then, I might write a vector with like a hat over it. So like later on, we're going to see IJK, and I will very often write those with a hat over it. But the point I'm making right off the bat is that whenever we're utilizing, let me go back to this. Whenever we're expressing vectors in this class and we're doing our hand computations, I do not want to see just F. I want to see F with an arrow over it, or F with some similar, because I want you to be able to differentiate what is a scalar and what is a vector. And that's actually really important throughout this semester. Okay, now graphically or mathematically, however you want to look at it, vectors are generally defined by 3 data points. So first off, this would be an example of a vector. Okay, so the first thing that we need to know is the point of application. So where we're applying, if we're talking about forces, let's say where we're applying the force. So let's say we're applying it here. We need to know the magnitude. So we'll say the magnitude is 10 pounds. And then we'll say the direction. Or the orientation. So if you ever hear me use the term direction or orientation, I'm basically referring to the same thing. So what we'll do is we'll say for this vector has a magnitude of 10 pounds and its orientation is 30 degrees counterclockwise from the horizontal axis. And that is a representation of this vector. So whenever we're actually drawing vectors, either by hand or in some illustration, we tend to draw them to scale. And there's actually a little bit of a baked-in meaning into that word scale, because that's what scalars do. Scalars scale vectors. That's kind of their whole point. So does that kind of make sense? Okay. So let's talk about what scalars can do to vectors. Okay. So if I have some vector, let's say this vector here, vector P. If I have this vector and I multiply it by a scalar, okay, what it's going to do is it's going to change the magnitude of that scalar. Now, it's not really going to change the direction unless you multiply it by a negative number. It will flip the direction, but it will not change its line of action or the sense of the force. In other words, if the line of action of the force was like this, A scalar isn't going to change that. All a scalar is going to do is either going to say it's pointing this way, or if it's negative, it's pointing in the opposite direction. Okay? So far, so good? So, for example, if I have, let's say, this vector p, and I multiply it by 1.5, so the scalar is 1.5, what I'm doing is I'm taking this vector and I'm increasing its magnitude by 50%, or multiplying it by 1.5. But again, I'm not changing its direction. Now, if I were to multiply it by -2, I am increasing its magnitude. So if this was representing, let's say, 25 pounds, this one's going to represent 50 pounds. But because it's negative, it's flipped along that line of action. It's not changing the orientation. You can sort of think of it's the same magnitude. It's just negative magnitude. So it's along that same line of action. Sound good? All right. Now, this first module of the class, and really the primary mathematical skill that you need to be able to employ between now and when we have our first celebration of learning. Remember, we don't have exams in college, we just have celebrations of learning. And so between now and our first exam, what we're going to be focused on is adding vectors, taking vector A plus vector B. And so mathematically, during our second exam, we're going to be concerned with multiplying vectors. Right now, we're not worried about that. Multiplying vectors really doesn't have a physical meaning unless the forces move away from a common point of reference. So what I mean by that is this. So this module of the class is called the statics of particles. And all that really means is that what we're going to first concern ourselves with in this course is how to deal with situations like this. In other words, we have a series of forces and they are all meeting at a common point. So here's force P, force Q, force S, and they're all meeting at point A. Okay? And we're going to call that a particle. Another name for that scenario is a concurrent force system. In other words, all of the lines of action of those forces all meet at a common point. Later on, we will deal with non-concurrent force systems. How do we handle situations where they don't meet at a common point? And so between those two, you sort of get the big picture. Now, what we're going to do starting out is we're going to learn how to add two vectors. And then later on, we'll say, well, what if it's 3 or 4 or 5 or 6? How do we add n vectors together? And so in this lecture, what we're going to do is we're going to borrow off of the skills, the rust that you shook off with things like the law of sines and the law of cosines. But you're going to see, while that's okay for 2 vectors, when we start getting into 6 vectors, it wouldn't work. It would, but it would just be computationally cumbersome. So we're going to develop a different way of going about it, and that's where I, J, K, and some of our standard notation for vectors will come into play. Okay. Now, a couple things about the adding of vectors. If you have vectors that are all along the same orientation, you can add them by combining their magnitude. So, for example, if we had 3 folks here pushing a car and they were each pushing with 60 pounds of force, assuming I know that they're not literally on top of one another, but assuming for the sake of discussion that they were all along the same line of action, if each of them were pushing with say 60 pounds, I could say the resultant of that situation is that they're pushing this car with 180 pounds of force because there's 3 of them each pushing with that same magnitude. Another idea is, like for example, if we're talking about tug of war, we have a group of folks on either side of the rope, and they're each applying a different force, but they're all applying that force along the same line of action. So basically, what we can do is just add up their magnitudes. And if we wanted to treat this mathematically, we could determine who wins. So, for example, we could treat everybody in blue as exerting, let's say a positive force, and everybody in purple exhibiting, let's say, a negative force. Then we just add up all the numbers. And if the resultant number is, let's say, negative, then the purple team is winning, right? If the resultant number is positive, that means the blue team's winning. If the resultant number is 0, that means you're just sitting there and nobody's winning, right? They're all yanking, but nobody's actually winning. And we can do that as long as they are along the same line of action. Sometimes we'll call that the line of action or the sense of the force, but the idea that we're looking at, for example, this tug of war example, everybody is applying a different force, but they're all applying it in the same direction, in the direction of the rope, as it were. Make sense? What happens though, if somebody takes that and they start applying it in another direction, well then we can't just start adding vectors. So how do we add vectors generally? Okay, so by definition, we add vectors, and this is where we get into the math of the situation. We add vectors according to basically the properties of parallelograms. So the idea is that let's sort of focus on this lower left example over here, this vector P and this vector Q. So let's say for the sake of discussion that I have a vector P and a vector Q, and they're both being applied at this point. The idea is that what I can do is I can take these vectors and I can start graphically arranging them in a tip-to-tail fashion. Now that doesn't mean I can take the vectors and start turning them. The idea is that let's say here's vector Q, I can take vector Q and move it over here. So the idea is that vector P gets me from here to here, vector Q gets me from here to here. This is the resultant. This is the sum of those vectors, and that's what I'm after. So the idea is that instead of having two vectors, two forces, I can replace that with a single unique force, which we call the resultant. And that works if you have two vectors or you have a bunch of vectors. So here's vector P, here's vector Q, here's vector S. So I can replace those three vectors with just this one down here. Now, one of the nifty parts about the addition of vectors is that because we're following this graphical rule, what we find is that vector addition has the property of commutativity. Okay? Now, commutativity is a very fancy word for just saying that the order of operations doesn't matter. So in other words, here's vector P, here's vector Q. Okay? What I could do is I could take vector Q, stick it up here, here's the resultant. Or I could do it the opposite. I could take vector P, move it over here, get the same answer. The best way of describing it, I think, to put it in and give you a little bit more realistic example, let's say I'm on foot and I'm on the corner of Hal Greer and 3rd. And I want to get to the rec center. Okay? So there's a couple ways of doing that. I could walk along 3rd Avenue and then cut 20th, right? That'll get me to the rec center. Or walk along Hal Greer and then walk along 5th. Gets me to the same point, right? I can either walk the short path, then walk the long path, or walk the long path, then walk the short path. I'm going to get to the same point. In other words, when I'm adding vectors, it doesn't really matter what order I add them. Mathematically, I can take vector P plus vector Q, and I get the same thing if I take vector Q plus vector P. The order of operations does not matter. And I make that point because for vector addition, the order of operations doesn't matter. For vector multiplication, there's two types of ways of multiplying vectors, and when we talk about cross products, the order of operations does matter. You cannot take P cross Q and get the same thing as Q cross P. It doesn't work out that way. So you have to maintain the order of operations. It's why we define moments in a very, very particular way later on. Does this make sense conceptually? Everybody good? Let's do some math. I think I've talked enough about some of the underlying theory and the underlying concepts. I want to actually do a problem. Okay, so this is among the most fundamental and necessary skills that we need to develop in this course. Now, we're going to do this problem. I don't want to say it this way, but there's really no other way to get around it. Today, we're going to do this problem the hard way. Later on, we're going to develop an easier way of going about it. But I kind of want to do it this hard way first because I want to submit your understanding, and I really want to make sure that you're comfortable with your trig skills. Because if you can do the trick associated with this problem, then the stuff we're doing later is going to be a breeze. So trust me, I have a method to my madness, as it were. Okay, let me pull up the notebook because this is all here in the notebook as well. So, okay. So I have here to use both a graphical and trigonometric approach to determine the resultant of the two forces applied to the hook shown. So let's just sort of use a little bit of common sense and see if we can understand what's going on here. Okay, so I have this, hook screw here, and I have these two forces being applied to a common point. So I got 600 newtons being pulled up about like this, and I got 900 newtons being pulled up somewhere about like this. So what I want to do is I want to replace those two vectors with a single vector that has the same equivalence. So if I was a betting man, what I would suggest is that that resultant vector, I don't know, is probably going to be pointing somewhere about like that. Is that a fair statement? Like if this one's going this way and this one's going this way, the sum is probably somewhere in the middle. And its magnitude is probably going to be bigger than these two, right? It's going to be bigger than 600 and bigger than 900. I don't know how much, and it's probably not going to be 1,500 because we're going to have some trig involved in there, but it's going to be about like this, and it's going to be bigger than these two. So before we start doing any math, does that, just in your gut, does that kind of make sense? Okay. Now, the way that we're going to handle this is we're going to do this in a tip-to-tail fashion. So we're going to take one of these vectors and sort of slide them over like that. So the way that I'm going to handle that is sort of conceptually, I'm going to have a 900 Newton vector, and I'm going to take this vector. So let's say it's like this. Let's say that's how we're doing it. And the way I'm going to do this is, let me see if I can handle this way. See if I can do it like this. So the way I'm going to do this is I'm going to take this vector and sort of move it like that. You see what I'm doing? So here's how the problem is defined, and I'm taking the vector and I'm going to move it like this. So the goal is to try and find this resultant. Okay, so this is what I'm trying to find right here. So we'll call this R, and again, I'm going to put a little arrow over it because it's a vector, but that's really what I'm trying to find. So does that make sense, that concept? Okay. All right, so let's see if we can handle this with some graphical deduction. Okay, so, all right, so let's look at a graphical diagram. Now keep this in your head, okay? So we've got one vector that's 30 degrees off the horizontal, and then one that's how many degrees from the horizontal? This vector right here, how far is it from the horizontal? 75 degrees. Not the 45 is how far it's measured from this one, but from the horizontal, it's 75 degrees. Everybody okay with that? Keep that in your head. Okay, so let's do some things. All right, so let's start off with that first vector. Let's put that, I don't know, right here. And I'm doing this by hand. I'm also going to try and do my best to draw this to scale. I know I'm sitting here on a screen, but I'm going to do my best to try and draw this to scale. Now, this is a 900 Newton vector. And what I'm going to do is down here on the bottom, I'm going to sort of draw myself a little bit of a coordinate system, about like that. And this angle right here is 30 degrees. Does everybody agree with that? Okay. So let's also put myself a little coordinate system here. What can you tell me about that angle? This one right here. It's 30 degrees, right? Because what do we have? We have two parallel lines cut by a transversal, right? With me so far? Okay. Now, let's take that next vector and tip to tail. Let's put it right here. So let's see what we got. Okay, I'm going to try and keep the scale accurate. That's probably pretty good right there, because this one was 600 newtons. So it's smaller, okay? And what do we know? What do we know about this angle? 75 degrees. Okay? So if this is 75 degrees, what's this one? Say again? 15. Because this is a 90-degree angle. So this is 15 and that's 90, right? So could I say that this is 105 degrees? Would that be a fair statement? So what we've got to find then okay, this doesn't like me. So that's the resultant we've got to find, right? Well, do you think that I could probably take this problem and maybe simplify it a little bit? And what I mean by that is this. I've got essentially a triangle where this angle, what is this angle? Maybe 135 degrees, and this is 900, and this is 600. Starting to look like a problem that we had on our last homework assignment, isn't it? Starting to look like a law of sines, law of cosines problem, isn't it? Now, so that we're clear, and I know that my artwork is probably horrible here, but let's make sure that we're clear on a couple things. Again, this angle is 30 degrees, right? Okay. I'm going to solve for this magnitude, or this is that vector, and I'm also going to solve for this angle right here. And I'm going to call this angle alpha. I just need to give it a name. It doesn't really matter. I can call it X. I can call it beta. I can call it what have you. I'm just going to call it alpha. No reason. Just I felt like using alpha this morning. Okay. Now let's deal with the magnitude of R. So remember, this is a vector. All right. So vectors are defined by two quantities, a magnitude and a direction. So let's start off with solving for the magnitude of R. Let's put that down here. Okay, and a note, just a little note here on some notation. So the magnitude of R can be represented like that. So in other words, imagine a vector with like absolute value signs. But sometimes you will see that I write the magnitude of R just as that, because the magnitude of R is a scalar, right? So this might, every now and then I might say, well, this is superfluous. I'm just going to write it like that. So if you see me use this notation, this is what I'm talking about. Okay. Now, the way that I'm going to solve for the magnitude of R is to utilize the law of cosines, right? Look at the triangle, okay? Remember, the law of cosines is more readily useful when your three known quantities for the triangle are all hugged on one side. In other words, I know the length of this side, I know the length of this side, and I know this angle. I want to solve that side. These three pieces of information are collected on one side. That's a law of cosines problem, right? So what I'll do is I'll say, okay, well, in order to apply the law of cosines, what I got to do is I got to say, okay, we have 900 newtons squared plus 600 newtons squared minus 2 times 900 newtons times 600 newtons times the cosine of 135 degrees. Then I got to take the square root of that whole thing, right? Because all I'm doing here is just a squared equals b squared plus c squared minus 2bc cosine a. That's all I'm doing. That's just the law of cosines, right? I think I can write that part better. Sometimes I get too concerned about the calculations being neat, but I want to make sure y'all can read them. So, can somebody break out your Casio FX115ES Plus or similar scientific or graphing calculator and tell me what you get for all this when you check it out? Say 1390. Let's give it a couple more. Let's say 1390. We'll give it 2 decimal places. What'd you get?
5.7.
5.7. And the units for that are newtons. All right. Do I have a second on that? Okay. We got a couple people raising their hand. Okay. Good. So I don't want to just barrel ahead. I want to make sure that what I just did makes sense. I don't want to just be that guy who throws stuff on the boards like, oh, everybody gets this. If there was something around here that was confusing, let me know. Okay. Remember, whether it's scholarships, loans, out of pocket, your parents, somebody's putting cash money on the table for you being here, and I want to make sure you understand this. So, everybody good? Okay. All right. So, how do we define a vector? We need a magnitude and a direction. The magnitude of this resultant vector is 1390.57 newtons. Does that kind of pass the smell test based on the way the vectors, correspond? I kind of think it does. Okay. Now, that's good, great, grand, and wonderful. But what about the direction? Okay. Well, the direction involves its orientation. So the direction, I'm going to find the direction of this vector r by solving for alpha. Okay. Now, there's a number of different ways of going about doing this. Personally, I try and utilize the law of sines whenever I can because I think it's easier. I think the formula is smaller, and I'm lazy. So what I'm going to do is I'm going to say that the sine of alpha divided by this, divided by 600 newtons, has got to equal the sine of 135 divided by the magnitude of r. But we just figured out what the magnitude of r is, right? We just did that. So now I can solve for alpha. So let me put that down here. So the direction of r. So we'll say that the sine of alpha divided by 600 newtons has got to equal the sine of 135 degrees divided by 1390.57 newtons. So therefore, how do we go about this? Let's multiply the 600 newtons over here, right? So we'll multiply both sides by 600 newtons. Here, I'll do that. Oh. All right, so over here we have the sine of alpha, and over here we have 600 newtons over 1390.57 newtons times the sine of 135 degrees. And so alpha is just the sine inverse of all this. Somebody tell me what you're getting for alpha. 1776. Eric, do I have a second on that? I'm a dork. It's okay. You can edit. Again, the dad jokes, y'all are just gonna have to get used to them. I mean, they're gonna be coming out pretty strong. Okay, so alpha is 17.76. Everybody okay with that? Now, I want to be crystal clear in terms of what alpha is, because when I express my final answer, I want you to understand how I'm doing it, okay? Remember, here's the point, okay? So we had a vector going like this, and then our resultant was going like this, okay? Now, here's the beginning. Remember, we said that this was 30 degrees, and this angle right here is alpha, which is 17.76 degrees. Everybody okay with that? Now, when I express vectors, okay, what I typically try and do is I try and say, okay, here's my answer. Okay, here's the vector. Vectors are defined by two things, a magnitude and a direction. So let's start off with the magnitude. The magnitude in this case is 1390.57 newtons. Now, as for the direction, I want to express the direction in a fashion that everybody can understand regardless of the problem. So what I like to do is I like to say, okay, tell me what the the direction is with respect to the horizontal. So in other words, here's the horizontal, and I go up so much to get to my vector. And how much do I go up from the horizontal to get to my resultant vector? It's not 17.76, 47.76. That way it's a common frame of reference that we all know. So this is the direction. What do you think? Not too bad, right? It shouldn't be. I mean, that's the whole purpose of that homework assignment that you did this weekend, was so that when we start getting to this point, it's like, oh, here's this law of cosines and law of sines thing that haven't used for 4 years. It's like, no, let's actually go through and use it so that when you come to class on Monday, oh, now I'm starting to see the point, okay? Any questions on the concept? Okay, so I want to talk a little bit about logistics. So you're going to have a homework assignment that's going to be very similar to this. I'm going to give you a problem where there's two vectors and you need to express the magnitude like this. So let's talk about the specifics. So I want you to, you're going to do this either on quad paper, on 8.5 by 11 letter paper, what have you. If you have like a Surface or a tablet or something like that, and you can take your homework and convert it into a PDF and you want to use that, totally fine with me. I'm totally okay with that. As long as it's legible and I or myself or the TA can easily discern it, that's totally cool with me, because I know that there's a fair amount of students these days who don't even have notebooks. They just do everything on their tablet. That's fine too. You're going to take that, convert it to a PDF, upload it to Blackboard instead of doing the time quiz. I set the upload and whatnot to where you can upload an unlimited number of times. So if you upload the assignment, you go, that's wrong. I messed up a calculation. Fix it, upload it again. And I grade based on the last upload. Okay, so if you upload this thing 12 times, I will grade your 12th submission. Okay, so I try and set it up similar to the quizzes. The only difference is, I mean, you're not going to get an automatic grade on this like you would the quizzes because you're not inputting a value, you're just uploading a PDF. And that'll be how the homework assignments are for the rest of the semester. Because, I mean, they're going to be like this. They're going to be, they're not going to be super, super involved, but there's going to be calculations. There's going to be steps to it, and so on and so forth. Sound good? All right, one last thing. I want to make sure and say this at the end for those of you that came in a little late. I haven't yet started tacking on late penalties for the attendance, but I'm going to go ahead and start doing that. The way I'll handle it is whenever you scan scan the attendance sheet, it timestamps when you do it. So if it's a minute or two after class starts, that's no big deal. But if you weren't there to scan your QR code at the beginning, that's where I'll start to assign the late penalties. I'm going to go ahead and pull this back up and stop the recording. With that, that's all I've got, everybody, and I will see you all on Wednesday.